to recursively compute the predictors. So the first one we call the DL algorithm, and the second one is the innovations algorithm. So today we'll do the innovations algorithm. Okay, right here. So true or false. So we can apply the DL algorithm to a stationary time series with zero mean. Yes, no. So the DL algorithm so you can use this one for any zero mean stationary time series. And innovations algorithm, so still we need zero mean process, but it could be stationary or non-stationary. So this is any process which need zero mean, and then the ACF function we call this time we call kappa ij. So that's the covariance between yi yj or yt ys. So just the covariance function. And then this covariance function must be non-singular. So means you can find the inverse of this variance covariance matrix. So here's the predictor forecast. So what do we need here? So we need a coefficient theta nj. So theta n1 to theta nn. Remember, we have data from y1 to yn, right? That's the data available. So we have data y1 to yn, and we want to predict the next few values. So n plus 1 hat, so this is one step ahead prediction. So h equals 1 here, one step ahead. So one step ahead, so we need to, so this is for linear predictor, right? So linear predictor, we have coefficient for each data point right here. So this is coefficient, coefficient, coefficient. And then, so in DL algorithm, we have something like, see, we have coefficient for each. So this is our data, right? In innovation algorithm, so instead of use the original data, we use say yn minus yn hat. So this is called innovation. So this is called innovation. So that's the why this algorithm called the innovations algorithm. Okay, and then the same definition for mean square prediction error. And we have formula here to calculate this predictor. And kappa function is the ACVF. And this is for the data here. Okay, so again, this one's called innovations, and we have if y1 to yn, then we have n innovations, and innovations are uncorrelated. So this is nice. So we have uncorrelated innovations. And again, the DL algorithm gave the coefficient for yn to y1. Innovations algorithm gave the coefficient for innovations, not the original data. Okay, and with this formula is for the mean square error. Okay, so Now just do one example. I need this formula here. Okay, so this example is MA1. So MA1 here. So theta is negative 0.9. This is theta negative 0.9. And sigma e squared. So this is 1 here. And then we know MA1 is stationary, right? So this is stationary. In kappa function, if it's stationary, so if it's stationary, and then this kappa function basically just gamma k here. So gamma II, so gamma II means covariance between the yi, yj. So I and j equal, and this is variance, right? That is gamma 0. So gamma 0 for MA1, this is the gamma 0 for MA1. Okay, so we plug in the number for theta negative 0.9, take square plus 1. And then the sigma e squared is 1, so 1.81. So that's the gamma 0, 1.81 for this MA1. So we did the same MA1 model before using the DL algorithm, right? So this is the gamma 0. And then for gamma I plus 1, so if the time lag is 1, see, I plus 1 and I, the time difference is 1. So this one is gamma 1. So gamma 1 theta sigma e squared. So this is negative 0.9. And then for other gamma k or other autocovariance, see this one I and j, the time difference, if it's larger than 1, so just like for MA1 rho k or gamma k equals 0 for k larger than 1. See, if the time difference is lag is larger than 1, and then this is like gamma I minus j. Gamma I minus j. So this is equals 0. Okay, so that's a kappa function. And so next, we want to calculate. Okay, so we start with, so this algorithm, so we start right here in the order. We solve all the coefficient in this order. Calculate V0 and theta 11, V1. Okay, so in here, let's see, we start with V0, and V0 is right here. So V0 is kappa n plus 1. Start with n equals 0, so that's 1. And minus, so this term is 0. This term is 0, and then we calculate theta 11. So we have to use this formula to calculate theta 11. Okay, theta 11 means, see, if you see the subscript here, means n equals 1, n minus k equals 1, right? So theta 11 subscript here, so n is 1, n minus k equals 1. So if n equals 1, n minus k equals 1, so k equals 0. And then we plug in, say, so n equals 1, k equals 0 to this formula right here. So n plus 1, that's 1, k plus 1, so n plus 1, that's 2, k plus 1 is 1, and k here is V0 inverse. And k equals 0, 0 minus 1, negative 1, j from 0 to negative 1, so this term is 0. Okay, and then we calculate V1. So find theta 1, 1, okay, and then you have, once you found theta 1, 1, so in this formula right here, n equals 1, right? So we have only one term, so that's theta n, which is 1, so n theta 1, 1 times y1 minus y1 hat. So y1 hat is 0 again, because when you have no data, we use the mean to estimate the y1. So y1 hat is 0, because mean is 0 for this process. So so we just use this equation to recursively estimate all the covariance coefficient here. So after you do V2, and then you calculate 2 coefficient, and you do V3, and so on. Okay. So this one here, theta k, so theta n minus k, theta k. So we start with n, for the MA1 example, we start with n equals 0. So y1 hat is 0 when we have no data, right? V0 just kappa 1, 1, that's the gamma 0, 1.81. When we have one data point, so n equals 1, and we predict y1 plus 1, so that's y2 hat. So we have only one data, right? One data point. So the theta 1, 1, y1 minus y1 hat. So theta 1, 1 right here. So this like, because in the formula we have n minus k, right? So theta 1, 1, n equals 1, k equals 0. So we use the formula. So we found, so V0, that's gamma 0. So inverse kappa 2, 1, kappa 2, 1, time difference is 1. That's gamma 1, right? That's gamma 1. So this one is gamma 1 divided by gamma 0. So this is rho 1 here. And V1, so this is gamma kappa 2, 2. So n plus 1, n plus 1. So that's kappa 2, 2 minus, so theta 1, so n minus 1 here, so we have two terms, right? The first one, so 0, 0, so that's gamma 0. What is the formula? Oh, I got an idea. So we have, so n minus k, that's kappa n plus 1, k plus 1, minus some j from 0 to k minus 1, theta k, k minus j, theta n, and then we in, can you unmute yourself? Okay. So n equals 1 here. So we need to calculate this one, right? So V1 here, so that's kappa K n plus 1, n plus 1. So that's n equals 1, so that's 2 and 2. And minus j from 0 to n minus 1, so n is 1, so that's 0. And we have only one term here. So the first one, gamma to 2, so the time difference is 0, that's gamma 0. Minus, so j equals 0 to 0. So j equals 0, so 1 minus 0, that's 1. So theta 1, 1 square, V0. We already got theta 1, 1, and V0, so just plug in. Okay. We do one more, n equals 2. Okay, we can forecast Y3 hat, right? So we can calculate Y3 hat. That's the forecast of Y3. Okay, two coefficients here. So we have n equals 2, we have Y1 and Y2, right? And then, so this is 0 here, we already know. And then we already calculate Y2 hat right here. So that's this term here. So we just need to find two coefficients. Theta 2, 2, so that's theta n minus k. So here n, if it's 2 and 2, so n equals 2. And n minus k equals 2, so k equals 0. For theta 2, 1, so here's 1, so n equals 2, k must be 1, right? And then we use this formula right here. So Vk inverse, V0 inverse, this V1 inverse. And kappa n plus 1, k plus 1, kappa 3, 1, 3, 2. And minus, so this k minus 1. So when k equals 0, this term is 0. When k equals 1, so that's j from 1 minus 1. So one term in here. Okay, so this is gamma 1, time difference is 1. And we have j equals 0. So theta 1, 1, theta 2, 2, V0. Okay, we can calculate that one. And V2 is right here. So that's kappa 3, 3 minus, so n minus 1, so n 2, so that's 1. So 0 to 1, so two terms here. So two terms right here. J equals 0, that's theta 2, 2 square V0 minus j equals 1, that's 2 minus 1 is 1, so that's theta 2, 1 square V1. So you just follow this one here and calculate V3, n equals 3. So Y1, Y2, Y3, we have only 3 points here, and we want to find Y4, right? And its mean square error. So this is the mean square error, and this is the forecast. And you can see, so this is exactly the same as the result from DL algorithm, right? Because it's a stationary time series MA1. So you use both algorithms, give you exactly the same result. Question? Okay, example 5. Okay, random walk here. We know random walk is non-stationary, right? So random walk is non-stationary. If you want to find a linear predictor for a random walk, we cannot use DL algorithm because DL algorithm only can be applied to a stationary time series. And the random walk is non-stationary, so we can use only one innovations. If you want to find linear predictor for random walk, you need to use innovations algorithm. So DL is not appropriate for this one. So random walk, so the random walk like this, so typically you can use this to model the stock price. So if you want to see tomorrow's price, stock price, so right here's today, if you want to predict tomorrow's, what is the stock price for tomorrow? Okay, so this is the one step ahead prediction, right? Okay, we can use two methods to find this tomorrow's stock price. The first method is the conditional expectation, right? The second is linear predictor. So conditional expectation predictor of next day's stock price. Okay, we have yn plus 1 hat. By definition of conditional expectation predictor, so this is the expectation of yn plus 1 given that's all data you have here. And then from random walk here, so yt is the sum of y noise up to time t. So this also has a recursive form like plus et, right? So this is another form for random walk. So yn plus 1 replace t by n plus 1. We have yn plus e t n plus 1. Okay, yn plus e n plus 1. Say from here, replace t by n plus 1. Let's put here. Okay, and then expectation of yn plus y noise at time n plus 1 given the data up to time n. See, if y is already given, so this yn just constant, right? So expectation is still yn. And then the second term, expectation of the y noise given data. See, because y noise is uncorrelated with the past y values, right? So time is n plus 1. So here's n minus 1 to n. So this one is uncorrelated with the data. So that equals expectation of x if x and y are independent, right? Uncorrelated. So we have so this term reduced to the expectation of y noise, and this equals 0 by definition of y noise. So basically, tomorrow's stock price, the predicted value, just today's price. Now, the mean square error associated with this prediction. So by definition, that's expectation of, so forecast error square. So yn minus 1, the first term, minus, so this is the forecast value, right? Take square. So by the definition of random walk, so yt minus 1 is et. So yn plus 1 minus yn, so that's the y noise at time n plus 1. And y noise varies is sigma e squared. Okay, so if you use conditional expectation predictor to predict for the one step ahead, and see the prediction just yn, and the mean square error is the y noise varies. Questions so far? Okay, now if we want to use linear predictor, so found the linear predictor of one step ahead, found one step ahead linear predictor. So random walk, see the variance of random walk equals t sigma e squared, right? and covariance between YT, YS, it depends on the TNS. It's non-stationary, right? TNS, so this, we need the smallest between TNS n times sigma E squared. So this is the kappa function right here. Sigma E squared times the minimum between I and J. Oh, I still need a formula. So this is the way we can calculate linear predictor by innovations algorithm. Okay, we start with n equals 0 and y1 hat equals 0 right here, and v0 is kappa 1, 1. In this time, you cannot say, okay, that's gamma 0, because so when you use gamma 0, gamma 1, so that's a notation for stationary time series. And random walk is non-stationary, right? So gamma 1, 1 means I equals 1, j equals 1. So minimum between 1, 1, so that's still 1, so that's sigma E squared. So kappa 1, 1 sigma E squared. And then we go n equals 1. So n equals 1, we need to find this coefficient in V1, right? So this coefficient right here. Okay, so V0 inverse, that's kappa 1, 1 times kappa 2, 1, minus this sum is 0. So that's a kappa 2, 1 divided by V0. Kappa 2, 1, kappa 2, 1. Okay, so the covariance or the kappa ij, so 2, 1 here, kappa 2, 1, so that's minimum between 2 and 1 times sigma E squared. So minimum between 2 and 1 is 1. So the kappa 2, 1 is sigma E squared. And V0 sigma E squared divided by V0 divided by sigma E squared, so that's 1. And so you plug in theta 1, 1, which is 1 here. So y1, y2 hat is y1. And then we calculate v1. So kappa 2, 2. So we have kappa 2, 2, minimum between 2, 2, so that's 2. So the first term, this one is 2 sigma E squared. And minus theta 1, 1 square V0, so plug in. So V1 is sigma E squared. Okay, and then we do n equals 2. N equals 2. Okay, so in the formula, basically you need a kappa 3, 1, kappa 3, 2, right? So these two values, kappa 3, 1, minimum between 3 and 1, so that's 1. See, this is a sigma E squared. Okay, see, right here is this sigma E squared. Kappa 3, 2. So kappa 3, 2, minimum between 3, 2 is 2. Okay, so this one right here, that's the kappa 3, 2. Okay, and then we calculate V3. So kappa 3, 3, minimum 3. So see, kappa 3, 3, that's 3 sigma E squared. And V2 is the same as V1, V0 sigma E squared. So you just keep doing this. So we get a yn plus 1 hat. So this is the last observation. And then Vn, the same, just sigma E squared. So in this case, the linear predictor and the linear predictor by innovations algorithm is the same as the conditional expectation predictor for this random walk. Questions? So before the conditional expectation predictor or linear predictor, we said in both two algorithms, we have the stationary mean 0 or non-stationary mean 0. And then there's just a general stationary time series. And then in this section, so we just want to forecast for ARMA part, data forecast for ARMA model. This is only for ARMA model. Okay. And suppose YT is causal invertible ARMA PQ process. Again, we need mean 0. So causal invertible ARMA PQ is a stationary. And we have the mean 0 here. And once again, so if it's a causal, you can write YT in terms of ET and past values. If it's invertible, you have ET in terms of YT and past values. And the coefficients, so we have psi j and pi j here. So the one step ahead prediction, conditional expectation predictor, okay, right here. So I skipped all the proof here. So I have proof here, but I delete everything here. Okay, so see this. Okay, that's negative. So pi j is from here. So if it's invertible, you can find the pi j, the coefficient, and then pi j goes to here. So this is the conditional expectation predictor. See, what do you have here? So when j equals 1, you have negative pi 1, yn plus 1 minus 1. So that's your yn, right? And the second term is negative pi 2. And j equals 2. N plus 1 minus 2, that's yn minus 1. And pi 3, you have yn minus 2. You have pi n, so you have y1. If you continue, so if you have pi n plus 1, and then you have y0, right? And pi n plus 2, you have y negative 1, and so on. Oh, that's all minus. See, this sum here is j from 1 to infinity. But in practice, we do not have data for, say, y0, y negative 1, y negative 2, right? When right here. So if this one is negative, we don't have data. So we have one called truncated one step ahead. So T here stands for truncated. So yn plus 1 ahead, so truncated one step ahead. So we need to put n here, not infinity, because we don't have yj when j is less than 0. So then the mean square error for one step ahead is just y noise variance here. But to compute this one, you need to know the pi j. So edge step ahead. So edge step ahead. Okay. So edge step ahead. Okay, you have yn plus 1 to yn plus h. Okay. So this is what you have. And then we have the formula for one step ahead. You can find this one here, right? And then you treat everything as given. You find n plus 2 ahead. So this is the one step ahead of y1 to yn plus 1, right? And then, so you treat everything knowing you forecast yn plus 3 and so on. So for yn plus h right here, this predictor, so the j from 1 to h minus 1, now you see here, what do you have here? So when j equals 1, okay, suppose h equals 3. You want to find n plus 3, right? And if you want to predict n plus 3. So you have data y1 to yn. You don't have yn plus 1, yn plus 2, right? So here you see you have when j equals 1, you do equal 3, so this is 2. So you have j equals 1 and 2. And you have pi 1 y n plus 3 minus 1, that's n plus 2. You put a hat here because you don't have it. You have to estimate first. That's negative. And pi 2, so yn plus 1 hat. So you have to use hat, the forecast for this two. And then, so you have everything else the same. So that's yn plus s minus j. So that's all your data here. So this part is for your data, and this part is for the forecast here, for this two here. And then the same idea, we have truncated edge step ahead. So infinity here replaced by n plus h minus 1. And then the mean square error, sigma e squared, see j from 0 to h minus 1. Okay, now this coefficient is from, so this phi square is from here. Oh, sorry, from here. See psi j here. And you need this one for the mean square error. So mean square error right here. So this one is from the causal relationship. And see, your forecast error is uncorrelated with your data y1 to yn, but the forecast errors, see, this is a forecast error for yn plus h. This is forecast error for yn plus h plus k different time, and they are correlated. Forecast error means 0, but it's correlated. Okay, so we have two examples here. So the first one, again, this is MA1. Okay, in general, sorry, just theta. So in general, you have MA1. Theta absolute value less than 1 means it's invertible. In MA, it's always causal. So MA is always causal, and theta absolute value less than 1, so this is invertible. So we can use all the result from the forecasting of ARMA model, causal invertible ARMA. Okay, now we want to find the one step ahead prediction and the mean square error. So for MA1, so if you look at nodes, you have this one right here. So the pi j is given for MA1. So that's just negative theta to power j. Okay, and then one step ahead. So you just need to replace, this is the pi j. So negative theta to power j. So once you know the theta value, and then you can calculate everything here. It mean square error for one step ahead is always the variance for white noise. So that's sigma e squared. Okay. So that's example 6, example 7. I think this is similar to, this will be similar to your homework problem. Okay, so you don't have homework this week because you need to study for the test, right? Okay, so no homework this week. So if we have AR1 process, so AR1 here, so this is the phi1. And how about this, the constant here? So this is, we call the constant term in AR1. And this is not equals to the mean of YT. Mean of YT, because this, okay, now see this AR1, phi1 absolute value less than 1. So this AR1 is causal, right? And AR1 is always invertible. So this AR1 is causal invertible. Okay, if it's causal stationary, so the mean, say we said mu. Stationary, so mean is a constant, right? And this constant term is not equal to the mean. So there's a relationship. Okay, so right here. So A is the constant term. And mu is the process mean. And this phi here is negative 0.5. And then we can, so we know A, so that's 16.2. We know phi negative 0.5. And so we can solve for the process mean. So the process mean is 10.8. And for AR1, what do we know? So we know almost everything for AR1. So for AR1, we know the psi j is phi power j. And we know pi 1 equals negative phi and pi j equals 0 for all j larger than equals 2. Okay, so this one is given before, right? So how do you know this too? Here. So pi j, so if it's invertible, you can have the form for pi j. Sorry, invertible, we need you can write ET in terms of YT. So we have pi j here. Okay, so the first term is start with pi j from 0. Okay, the first term is pi 0 YT. And second term is pi 1 YT minus 1, right? And pi 2 YT minus 2. So in this form right here, so we always set pi 0 equals 1. So means the first term is YT. YT plus pi 1 YT minus 1, YT minus 2, pi 2 YT minus 2, and plus. Okay, so AR1 here. See AR1 process here. So for AR1, suppose don't worry about the constant or the mean function. So this AR1 here is equivalent to subtract the mean equals phi is negative 0.5. And YT minus 1 minus mu plus ET. And now, what about ET here? So in the form right here, so the YT is mean 0. If it's not mean 0, you have to subtract the mean, right? Okay, so see this ET right here. So this ET equals YT minus mu. YT minus mu plus 0.5 YT minus 1 minus mu, right? So for this one, we have ET equals YT minus mu plus 0.5 YT minus 1 minus mu. That's it, right? So if we compare this two, and for YT minus 1 term, or if you have mean, so each term minus mean, each term minus mean. Okay, so the coefficient for YT minus 1 minus mu, so that's pi 1. So pi 1 equals here, right? 0.5. So this is pi 1, 0.5. In pi 2, we don't have yt minus 2 terms, so this is 0. So everything else is 0. So we have pi 1 here. So 0.5, 0.5, so phi 1 or phi is negative 0.5. So this is negative phi. In pi j, everything else is 0 for j larger than equals 2. Okay. So we have phi negative 0.5, sigma e squared equals 1. Okay, we got everything, so we are ready to calculate the predictor forecast and their mean square error. Okay, so part A, so find the 1 step ahead, part 2, 2 step ahead, part 3, 10 step ahead, and their associated mean square error. And also yn is given. So the last observation is given. So when h equals 1, see in all these formulas here, we assume, say, mean 0, right? If mean is not 0, we subtract the mean first, do the forecast, and then after that we add the mean back, because mean is just constant. So we have, okay, right here. How about h equals 1? So here you have to subtract the mean first, right? In the 1 step ahead predictor. So subtract mean here, you have to subtract mean from each y value. Okay, so yn plus 1 hat, j from 1 to infinity. So negative here and pi j. So we have only one non-zero pi j, right? Which is pi 1. So negative, so in this sum, we have only pi 1 term, one term in here. So the first one is pi 1, and here j equals 1, so that's yn minus mu. Okay. And then pi 1 is negative phi, right? So negative, negative, positive, so that's phi yn minus mu here. And then plugging all the numbers here. So this one here, so 1 plus 1 hat, so we move this mean to this right hand side. So we have mu plus phi yn minus mu, right? And you have mu here and minus phi mu plus phi yn. And then this again just your constant term. So in phi here, yn here. So basically in this formula, we keep right here. So the forecast yn plus 1 hat, we have, so this is our constant term here, in minus 0.5, minus 0.5. So to predict 1 plus 1, so here we have 1 here. So basically we keep this form here, put a hat here, and we don't have this term. So that's 1 step ahead prediction value here, 10.1. And the mean is 10.8. The mean square error. So 1 step ahead, so that's sigma e squared. So in this case, that's 1. And 2 step ahead. So 2 step ahead, so this is the formula right here. So h equals 2. So h minus 1, so the 2 minus 1. So in here, start from edge here to infinity, right? And then we don't do infinity, or you put it n minus h plus 1 something, you put something right here. But in this case, because all pi j larger than equals 2 is 0, so this term is 0 anyway. So we only have the first one. So j from 1 to 2 minus 1 is 1. So only 1 here. So negative pi 1 j equals 1. So that's yn plus 1 hat minus mu. And pi 1 is negative phi. So yn plus 1 hat minus mu. And so we have, right here. That's a phi yn plus 1 hat minus mu. And we move the mu to the right hand side, so yn plus 2 hat. So this is mu here, and plus this one right here. And combine the constant term, that's give you, combine all the mu terms, we have the constant here, and plus phi yn plus 1 hat. So this is exactly the same formula, right? The same form. So when you do yn plus 1 hat, so they have the constant term plus phi times the previous value, that's yn. And for yn plus 2, you have constant term, phi same, and this is the last. We don't have data, but we have the prediction, right? We use the prediction for yn plus 1. So we plug in everything, so we have this is the value for the forecast. And mean square error. So this is something new. So mean square error. So this is definition, and this is the result we have. So this is h minus 1 here, and psi j square. And for AR1, we know psi j is phi power j here. Okay, so j from 0 to h minus 1. So 2 minus 1, that's 1. So we have 2 terms here. So sigma e squared is 1. And then, okay, psi 0 by definition is, that's 0. Like pi 0 equals 0 equals 1, and psi 0 equals 1 too. Okay, so you have 1 here, so that's psi 0 squared, so 1 squared, and plus psi 1 squared. Okay, psi 1 is right here. Psi 1 is just phi, right? Power 1, so that's phi. So that's phi n squared. So this is 1.25. So 1 step ahead mean square error is 1. 2 step ahead is 1.25. And okay, now when h equals 10, question on this one, h equals 2 step ahead. So now we do h equals 10, okay. Because pi j equals 0 for j larger than equals 2. So this one is nice 0. And in here, still we have only 1, right? Only 1 term here. So pi 1 is, there's a head here. Okay, pi 1 is negative phi. So that's, here is a phi. So yn plus 9 head minus mu. Right? And we replace this one by yn plus 8 here. Replace yn plus 9 head by minus mu. This whole thing. Equals phi, last one. So yn plus 9, so last one is n plus 8, right? Head mass mu. Okay, so this part is this one here. So we got another v, right? So just repeat until you got a yn. So the coefficient is v. So basically this is h here. H equals 10. So it's v power h and yn minus mu. Okay, so mu is 10.8 and 90.5 power 10 is almost 0, right? So this is almost 0. So the second term is just about 0. Okay, now you see if you do 10 step ahead forecast, so the forecast value just see close to the process mean, right? So this is the process mean. If you do say 20 step ahead, this is also just about the mean. So when as you go to infinity and you forecast value, just the process mean. Questions? Okay. So the mean square error for 10 step ahead forecast. Definition result for the MSE. So this is H right here. And sigma E squared. So for AR1 psi J is phi power J, right? Square. Okay. And then this sum here is geometric series. So basically you have the first term 1 in phi square, phi power 4 to phi power 18. And this is the formula, the sum for the geometric series. So 1 minus phi square is the common ratio, and 1 minus the next term here. So phi 20 is the next term, right? So 1 minus the next term. So this one here, so because phi, the power 20 almost 0. So that's 1 divided by 1 minus phi squared. So we have sigma E squared here. And you know for AR1, this is the gamma 0. So that's the process varies. So in general, so for large edge, your forecast value just a process mean. And your mean square error for this forecast, the long-term forecast, this is a process varies. So this is just the process varies. And this is true for all stationary ARMA models. So forecast approach to the process mean square error, approach to the process varies. So gamma 0 is the variance of YT. Sigma E squared is the variance of Y noise, right? Okay, so we have one more thing for forecast. So we call the update. If you have, say, Y1 to Yn, right? That's all your data. And then you can predict Yn plus 1, Yn plus 2. Suppose just do 2. And when Yn plus 1 is available, right? So once this is available, if Yn plus 1 is available, how do you update this Yn plus 2? This forecast for Yn plus 2. So we have only data up to time n. So this is your 2-step ahead prediction, right? And once Yn plus 1 is available, and then you should have Yn plus 1, n plus 1. So n plus 1 data ahead. So this is a one step ahead prediction of based on y1 to yn plus 1, right? So you have all data, you can start over. So just calculate this one as the one step ahead, right? That's no problem. But sometimes if you have, very, very large number here, the observations, you don't want to start over. So you just want to update this forecast. So update the forecast for say 1 plus 2 here. So you already have the 2 step ahead, right? From previous forecast. So you want to update this one here. Update forecast for 1 plus 2 using the old forecast for yn plus 2. So we'll do this update. Next Tuesday, right? Tuesday. Okay. So no homework this week. And then I'll return your homework 2 tonight, homework 3 tomorrow, and send you the take-home test tomorrow. And the test due Monday. So I think that's all for today. Any questions?
I have a question.
Okay.